All right, so we're going to talk about on this video how to graph parabolas. And parabolas are very, very common graphs, and definitely you should know how to graph a parabola going into calculus by hand, no graphing calculators. So let's get started. So we've been talking about the idea of using a base or a parent graph and then viewing a function like this as this base graph parabola shifted or translated or reflected perhaps. So we can do that in this situation. And just to remind you, your base graph, your most basic parabola, y or f of x equals x squared is your familiar U shape. And some points on there, which are easy to find, 1, 1, 2, if you square 2, you get 4. And of course, there's some symmetry here because if you square -1 or -2, you get the same exact y values as you do for +1 and +2. So there's definitely symmetry about the y-axis. And of course, the most talked about point on a parabola is this bottom point, this lowest point on a parabola like this, which is called the vertex. Okay. And a very, very important point. Often we want to know that for a parabola. So this graph here, we've been talking about this. This is a version of this parabola that has been shifted, and hopefully you recognize the x plus 3 based on what we were talking about before. That's plus 3 with the x. That is going to move the graph left 3. Remember, it's always the opposite. It's going to move it left 3. And -4 outside the squaring part is going to affect my y values. That's going to move my graph down 4. So every single point on this parabola has gone through this transformation. The easiest point to track, however, of course, is the vertex. So for this parabola, it's no longer going to be at 0, 0. It has been moved left 3, down 4. We'll just guesstimate that this is 3, -4. We know this parabola is going to bottom out right here. And before I finish this off, I want to find out some points like maybe a y-intercept, some x-intercept, so I can get an accurate graph. My y-intercept is easy. I'm just plugging in 0 for x. Most of the time you can do that in your head. If I plug in 0, that's going to be 3 squared, which is 9. 9 minus 4 is 5. So that's up here somewhere. And actually, just knowing that, I can finish my graph off because now I know it's going to climb up and cross the y-axis at this point. Go up in this direction. And see, now I know that when I find my x-intercepts, I can tell that they're both going to have to be negative. So let's go ahead and do that. So if my x-intercepts 0 equals x plus 3 squared minus 4, we can move that 4 over. To undo that square, we're going to do the square root of both sides, remembering that we have to do plus or minus, right? We want to get both of those intercepts. So we have plus or minus 2 equals x plus 3. If I move that 3 over, it's going to be -3 plus or minus 2, which gives me either -3 plus 2, -1, or -3 minus 2, -5. Okay, so there's that parabola. Now, as you can see, it's not too terrible to graph a parabola using transformations if it's written in a form like this. But oftentimes when we encounter parabolas that we need to graph, they are not written in that form. They are written as something like this: f of x equals x squared minus 2x minus 8. I know it's a parabola because it's got an x squared. I'm going to put the one we just did back up here. But see, I can't identify the shift. I mean, in order to identify the shift, I need to see like something x plus or minus something squared and then plus or minus a number here. By the way, This, if I were to multiply it out, x plus 3 squared, many of you can do that in your head. That would be x squared plus 6x plus 9. And then I have this minus 4. If I combine this, this is x squared plus 6x plus 5. See, when we get a parabola like this, we're seeing it in a form like this. And what we would like to see it in is a form like this, so we can identify the transformation. So there's a couple of methods that you can do to graph a parabola when it's written in this form, ax squared plus bx plus c. Method one, you're probably familiar with this, is to try to make this parabola look like a graphable form with transformations, and that's a process called completing the square. So the way that works, the idea is this: x squared minus 2x minus 8, that actually does factor, but I want it to factor into a perfect square, identical factors. So the way I do it is I just bump this minus 8 out of the way here. And what I want to do is put in a number here next to the negative 2x, so that not only does x squared minus 2x plus this number factor, it factors into identical factors so that I could write it as something squared. Okay. If you think about it, you can probably figure out that that number has to be 1, because x squared minus 2x plus 1 factors into x minus 1 times x minus 1, which means it would be x minus 1 squared. But there is an old way to figure out this number. If you're not sure what it is, you take half of this coefficient. So we're going to divide it by 2 and then square it. And that gives us this number here. Now, by putting that 1 there, I'm changing the problem. There wasn't a 1 there before. So it's very important after you put that 1 there to compensate by then immediately subtracting 1. Because if I put plus 1 minus 1, then I'm not really changing anything. That's just like a 0. So then these three terms factor into this. The minus 1 minus 8 gives me a minus 9. And now hopefully you recognize this as a parabola that has been shifted right 1 unit, down 9, which means I'm not going to draw any axes in here, but this would be a parabola like this, where my vertex would be at 1, negative 9. It went from the origin, it went right 1, down 9. So not too hard to complete the square. It does get more difficult, however, if you have a parabola with a leading coefficient of your x squared. When you complete the square, you need to have this just be x squared, not 3x squared, or at least it's more difficult that way. You can still complete the square, but here's what you're going to do. So I'm going to pull out this 3, but only from the first 2 terms. So I'm going to have this as x squared plus 4x. Just like the last one, I'm just going to bump that last number way out of the way, just get it out of the way. And we'll complete the square just on the inside here. So what number makes x squared plus 4x plus some number not only factor, but factor into a perfect square? Or just like last time, we can figure out that number by dividing this coefficient by 2, squaring that. That's 2 squared gives me 4. Maybe I should put this in a different color. Let's say, I don't know if you can see that. So that definitely completes the square. Now we do need to compensate just like we did on the last one, because I just put a 4 there. That's changing the problem. But here's where it gets a little bit tricky. It looks like I changed the problem by positive 4 here. But what is the real net effect of putting that 4 there? I have to consider that if I chose to distribute that 3 back in, that 4 is actually a 12, isn't it? 3 times 4 is really 12, which means to compensate, this is adding 12 to it. I need to then subtract 12. Convince yourself, take a second and convince yourself why I'm doing that, right? By putting that 4 there, it's really acting like a 12. So I need to subtract 12 to make sure I'm not changing the problem. Okay, after that, we can then rewrite x squared plus 4x plus 4 as x plus 2 squared. and I can take the negative 12 that I compensated with plus 1 and make it minus 11. This is a parabola that has, it does have a vertical stretch. If you recall, the number in front multiplied by your function will stretch your y values out. But in terms of the vertex, it's still affected mainly by the left and the left, right, up and down transformations. So this has been moved left 2, down 11. So this parabola would have a vertex at negative 2 because it went left 2 and down 11. So that's minus 11. So that's completing the square. And that's something you definitely should know how to do. There are times in calculus we do need to remember how to complete the square. For parabolas, though, these can get pretty messy. I made this one not too terrible. You can get some messy fractions and stuff like that. There is another method that is much faster and more efficient for a parabola to find the vertex, and it's based off this idea. Another way we could find the vertex of a parabola is to find the midpoint of the x-intercepts. Let me explain what that means. So it says the x-intercept, so let's go ahead and find our x-intercepts. If I set f of x equal to 0 and factor, I end up getting x, so it needs to multiply to negative 7, add to 6, so that's going to be plus 7 minus 1. If I set each of these equal to 0, I'm going to get x equals negative 7 or positive 1. And so here's the idea. Let me draw some axes in here. I definitely moved it more to the left because I can see negative 7 is my x-intercept furthest to the left, and then positive 1 over here, 1, 0. Now, the idea is this. We know this is an upward facing parabola. It's got a positive x squared. If it was negative, it would be going upside down. And these are the x-intercepts. But we also know that parabolas are nice and symmetrical. So if I were to imagine this parabola, where would the bottom of it be? Well, it would make sense the bottom of it would be right in the middle between these two x-intercepts, would be my vertex, right at the midpoint. Looks something like this, right? There's going to be some symmetry here. So it's halfway between negative 7 and positive 1. How do I find a number halfway between two things? I add them together and divide by 2. Now, this is only going to tell me the x coordinate of the vertex. So the notation we're going to use here is the vertex has an x coordinate, which I'm going to call v sub x, and it has a y coordinate, which I'm going to call v sub y. V sub x is right in the middle between my two x-intercepts, so I'm going to add them together and divide by 2. That's negative 6 divided by 2 gives me negative 3. Some of you probably could have figured out that, halfway between negative 7 and 1 is negative 3 because it's 4 units this way, 4 units this way. So I now know my x coordinate of my vertex. How do I find my y value? Well, if negative 3 is on my parabola, I can just plug that into my function and figure out my y value. So to find v sub y, I'm just going to do f of negative 3, which is negative 3 squared plus 6 times negative 3, and then minus 7. This is 9 minus 18. That's negative 9 minus 7. Looks like it's negative 16. So this vertex was negative 3, negative 16. Now, so that's kind of a nice way, right? But you can maybe see some downfalls with this method that you may think, well, wait a second, this isn't always going to work, right? For one thing, this worked out nice because my x-intercepts were nice, clean numbers here, right? No fractions or decimals or anything like that. Obviously, you've probably graphed parabolas where your intercepts are some messy things, so that might look kind of ugly, right, to do it that way. But there's another drawback that you might be worried about, that what if my parabola actually looked like this? What if right? Your parabola doesn't have to have any x-intercepts, right? What if your parabola lies entirely above the x-axis? There's still a vertex for this parabola, but it would seem like this technique I just talked about is not going to work, right? Because it all depends on finding your x-intercepts and finding the midpoint between those two. But surprisingly, it can work. We can still use this technique, which seems a little surprising, but let me show you. Okay. So I'm going to show you that we can use this midpoint technique for all parabolas. And so to prove that, I'm going to give you, this represents, right, every single parabola you could ever think of. F of x equals ax squared plus bx plus c. So my claim is I can still use the midpoint technique, even if my parabola doesn't have any x-intercepts. So let me show you. How do I find the x-intercepts? I set this equal to 0. Now, of course, I can't factor that because I don't know what a, b, and c are. So what do I do if I can't factor it? I use the good old quadratic formula, right? Negative b plus or minus square root b squared minus 4ac all divided by 2a. Now, if you think about it, depending on what a, b, and c are, do you see that there are actually two x-intercepts, right? One of them is negative b plus the square root of over 2a, and the other one is negative b minus the square root of all that stuff over 2a. And so what am I supposed to be doing with my two x-intercepts to find my x coordinate, my vertex? I'm supposed to be adding them together and dividing by 2. Let me put this back up here, what we did before. I'm supposed to take my two x-intercepts, add them together, divide by 2. So I'm going to do that. So I'm going to take negative b plus the square root of all of this stuff inside, divided by 2a, and add that to negative b minus the square root of all that junk, divided by 2a, and then divide it by 2. Notice that the numerator, these have the same denominator, right, of 2a. So I could actually combine this. I could make this negative b plus square root of stuff plus negative b minus square root of all this stuff, all divided by 2a. And instead of writing divided by 2, I could always think of all of this as times 1/2. Right, so this 2 dividing by 2 is the same as multiplying by 1/2. Now you can see why I didn't bother writing what was under the square root, because I have a positive and negative. That's going to cancel out. Negative b gives me negative 2b on the top over 2a times 1/2. 2's will cancel out, and I get negative b over 2a. And so let me write that. That's equal to v sub x. Perhaps some of you have seen this before, but this is a kind of a showing you why this is true, that the x coordinate of the vertex of a parabola is always going to be negative b over 2a. And so this is a handy thing to know in pre-calculus. When we get to calculus, we have other ways to find the vertex of a parabola, so it's not as necessarily as needed, but it is very useful in pre-calculus. So for an example, let me just show you here. So if I wanted to do, say I wanted to find the vertex of x squared minus 8x plus 3. If I want to find the vertex, I first find the x coordinate of the vertex using negative b over 2a. B is negative 8, so it's going to be the negative of negative 8 over 2. My a is 1. That gives me 8 over 2, which is 4. That's the x coordinate of my vertex. And just like we saw to find the y coordinate, all I have to do is just plug that in. I just do f of 4. 4 squared minus 8 times 4 plus 3. 16 minus 32 is negative 16 plus 3 is negative 13. So my vertex is 4, negative 13. You can even do it for some, crazy ones. So let's say I had negative 5x squared plus 10x plus 7. Okay, this is actually a downward facing parabola because it has a negative x squared. But I can still find my vertex the same way, negative b over 2a, so it's negative 10 over 2 times negative 5. That's negative 10 over negative 10, which is 1. And my y coordinate is just plug 1 into my function. If you plug in 1, that's just going to be negative 5 plus 10 plus 7. So that's 5 plus 7 is 12. So this vertex would have the coordinates 1, 12. So in one of my classes, you are now free to use negative b over 2a to find the vertex of a parabola. If you're taking Math 12, you might want to wait until they introduce that, or at least you could ask your professor to see if it's okay if you've used to use that. It's a fairly well-known formula. All right, thanks for watching.